Well, and now that we learned how to find the properties about how to find the properties from tables, let's just tabulate the first step. The first step was to find uh, the region of the material based on the given data. In the problems, we are either given temperature with a second property, or we are given pressure with the second property. If temperature is known, then the second property is going to be either of these four properties. It is going to be either pressure or specific volume, internal energy, or enthalpy. All right? You are going to find, you're going to first go to the saturation table of that material. Okay, let's say for instance, we have the temperature of the water. We go to the saturated water table. And then in that given temperature, we look for the second given property. Let's say that the second given property, as an example, is internal energy. I look at the internal energy and then I consider these three conditions. Oh, my apologies. I consider these three conditions, right? At the given temperature, I look at the second property, which is the internal energy. Now, look here. If the given internal energy is less than UF, which is the the internal energy of saturated fluid, then I have a compressed liquid. If the given internal energy is between UF and UG that you have in the table, means that you have a mixture. And if the given internal energy is larger than the UG, then you have superheated vapor, and so on and so forth. All right? Likewise, if we are given, if, my apologies, if you are given pressure, for instance, right? I know the pressure. You have to go to the saturated table, the tables of saturated water that are tabulated based on pressure. And then in that one, you will look for the given pressure. At the given pressure, you again go and look for the given property. For instance, here, let's say that we have pressure and internal energy. Again, if that given pressure, the internal energy is less than UF, right? Then I have a compressed liquid. If the internal energy that I have is between the internal energy of saturated fluid, UF, and saturated vapor, UG, then I have a mixture. And if the given internal energy in the problem is larger than what I find in the table for UG, then I have a superheated vapor. Okay? Let's go over some examples and we will see step by step how we can find the unknown properties of materials from the tables. Okay? Let me go over this example, for instance. Example one. Oh, my apologies. Here we go. Okay. Given is water at 400 degrees Celsius and the pressure is 10 megapascal. I want to find specific volume, specific internal energy, and specific enthalpy. Okay? In order to do this, I'm going to begin by looking to the textbook. From now on, what I want you all is to have your textbook beside yourself, and you have to try to solve each problem by yourself before watching the rest of the video. So, if you have the textbook, just pause, try to solve the problem by yourself, and then return and watch how I am solving it, okay? Pause it and give yourself some 10 minutes to solve this problem, all right? Then return and watch. Here is how I solve it. I'm going to have a step-by-step procedure that is applicable to all cases. The first step is this. I go and check the index of the textbook. You have an index. Let me share with you the textbook, and we can watch what we have here. Let me see, where is my textbook? Okay, here we go. All right, lectures. Here is a textbook, and Moran Shapiro, revision 8. Okay, I begin my work by finding the appropriate table. How to find it? First of all, the first step is to go all the way down and check the appendix. Here we go. Where is it? Yes. The index to tables in SI units. You see, you have two indexes here because I have the SI units. I look at this one. Okay, SI units. What I have is water. At the first step, you look for the table of saturated water. Okay, here it is. Properties of saturated water. Temperature table and properties of saturated water, pressure table. In this problem, I'm given temperature and pressure both. So I can use either of these two tables. Let's say, for instance, I use the I use the table of A3, right? A3, page 929. Let me go to page 929. Okay. This table is based on pressure. I'm going to check for 10 megapascal. What is this? This is bar. 10 megapascal is 100 bar. So let's go and check for 100 bar. Here it is. I have 100 bar here, and at 100 bar, I should check the second property, which is temperature. Look here. What is this temperature? This is the saturation temperature. If at 100 bar or 10 megapascal, the temperature is 311, then it is saturated water. Now my temperature is 400 degrees Celsius, right? So it means that I have superheated material. Now I know what the phase of my material is. I know that I have superheated water. The second step is to go and find superheated water tables. Okay, let me go back to the appendix and check for the superheated water tables. Here is properties of superheated water. It is table A4, right? Table A4, page 931. So the next step, I go to 931, superheated water. All right, my pressure, look here. These tables are tabulated based on pressure, right? And then at each pressure, I have various temperatures. I look for 10 megapascal. Let me see where it is. It is in next page. Yes, here we 130 bar, and the next page, page 933. Here we go. In page 933, I can find this value. Okay, here is what I have. Here it is. Okay, this is, you see here, this is 10 megapascal. At 10 megapascal, I look at 400 degrees centigrade. This is 400 degrees centigrade. I go all the way to here, and these are the properties, right? These are the unknown properties. So first of all, my phase is superheated water. Secondly, the table is this one, right? At page 933, I can read that the specific volume at this condition is 0.02641. And what is the unit for it? Cubic meter per kilogram. U, or internal energy in kilojoules per kilogram, is 2832.4. Enthalpy is 3096 and half kilojoules per kilogram, right? The last one is entropy, which we will discuss later when we talk about the entropy and second law of thermodynamics, right? Okay. Now let's see how we solve it. Right, here we go. This is actually what we found together, right? We go to table A4, right, for superheated water, and then at 400 degrees Celsius, you're gonna read what you have. For instance, U, right? U at that temperature is 2832.4 kilojoules per kilogram. All right. Okay. With that said, let's just think about something. And that is how easy our work was. The reason why it was so easy was that it happened for us that the temperature and pressure that we were looking at, we were looking for, were exactly tabulated. But in most of the cases, the temperature or the pressure that we are looking for is not exactly tabulated. For instance, in this table, what does happen if our temperature is 380 degrees Celsius, not 400 and not 360, something between these two? If that is the case, then we have to uh, interpolate, right? And how does the interpolation work? The interpolation works with this way. We tell that in our table we have 2 points. We know at 10 megapascal when the temperature is, for instance, 400 degrees Celsius, we have the U. Also, when the temperature is 360, we have internal energy. Now that we are in between, we do an interpolation, right? And that is an algebraic equation generated based on this idea that we assume from point 1 to 2 the properties are changing linearly. That is not exactly the case in the nature, but it's a very good approximation of the reality. Okay? I'm assume that, for instance, in this case, A is the temperature. I'm I'm neither at 360 degree nor at 400, right? I'm somewhere in between. Let me write it down. Assume that this is, for instance, 360 and this is 400, and I know you at this, right? Oh, sorry. I know you at 360 and I know you at 400. Now, what I'm looking for is U. I'm looking for this one. I'm looking for the U at 300, for instance, let's say 80, something in between these two. I'm looking for this value, okay? That 380 is given to me, okay? I want to find this one. I want to go from this point to this, and then from this to this. How to do that? You just need to write a proportion, and then you will find this formula. B equals B1 plus A minus A1 divided by A2 minus A1, and so on and so forth. Just keep in mind that what B and what A is. A is the temperature, is the property that you are looking for, that you are given, right? And B is your unknown property. Here it is, for instance, internal energy. All right, we call this the linear interpolation, and this is a single interpolation. Let's look at one example from this. Okay. Assume that we are given water at 10 bar and 215 degrees Celsius. Okay, now I want you to find the specific volume at this condition. Again, pause the video and give yourself 10 minutes to find the V at this condition. Okay, and then you can return and watch the video to see how I solve it. My solution, again, step one is to define what the phase of material is. And to do that, I need to go back to the table of saturated water. Here, I'm given the pressure and again temperature. I'll look for the saturation table based on the pressure, okay? Let me go to my textbook. Here we go. I go to appendix to find the table. All right, properties of saturated water based on pressure, page 929. I go to page 929. My pressure is 10 megapascal. Okay, 10 megapascal is 100 bar. So let me go to 100 bar. Here is 100 bar. The temperature that I have is, okay, let me see, let me double check the problem. Yes, 10, oh no, now my pressure was 10 bar, my apologies, 10 bar, here it is. My pressure is 10 bar and my temperature is 215, okay? The temperature is higher than the saturation temperature, which means that I have superheated steam, right? You can go back to the tables that we discussed, right? And in that one, check for the condition. If T is larger at a given temperature, at a given pressure, right? Pressure is 10 bar. If the temperature is higher than saturation temperature or Tsat, then you have superheated water. And that's the case for us. So again, let me go back and find superheated water tables. Here it is, table A4, page 931. I go to page 931. And at this page, I'm looking for 10 bar. Let me go for 10 bar. The next page, I have, here we go. I have 10 bar, right? Look at this one. At 10 bar, okay, I am given the temperature of 215 degrees Celsius. Look here. I have 200 degree and I have 240 degrees Celsius. But my number is something between these two, okay? I'm gonna use this row and the row after these two, right? 2 and 240, plug in it in the equation that I gave you previously, and then I will find the value, the unknown value. Okay? Let's see what the solution is. Here is the solution, right? This is my table, table A4. As soon as we found out from table A3 that we have superheated vapor, we go to table A4. And at table A4, I found this one. Look here. At 200 degrees Celsius, I know that the specific volume is 0.2060. At 240, it is 0.2275. Right? Look at this one. I've put them in this table. Right? This table is very important. Look at this table. Okay. I'm looking for 215 degree. Okay. With that said, what are my A1, A2, B1, B2. Okay, I said you B is our unknown. So B is specific volume. Okay, B is a specific volume. What is A? A is the known value. A, in my case, okay, B is, my apologies, specific volume. A is temperature. What's going on with this? Okay, this is a specific volume. Then, for instance, A1 in my case, A1 in our case is 200 degrees Celsius. A2, right, and corresponding to that, B1 is 0.2060, right? A2 is 240, and B2 is 0.2275. All right? And A is given to me. A is 215. B is what I'm looking for. We plug in these informations in the formula and we solve for the B, and here's the answer, right? V, specific volume, equals 0.2141 cubic meter per kilogram. All right? This is called single interpolation. We have a more complex condition, which is called double interpolation. Yeah, double interpolation happens when neither the temperature is accurate, is among the tabulated data, nor the pressure. For instance, assume that in this problem, we were asked to find the specific volume at 215 degrees centigrade and at pressure of 9 bar. 9 bar is not tabulated, right? We have 10 bar, we have 5 bar, but we don't have 9 bar. Nor 215 degrees centigrade is tabulated. We have 200 degrees centigrade and we have 240 degrees centigrade, right? We are somewhere in between 5 bar and 10 bar pressure-wise, and 200 and 240 degrees Celsius, right, temperature-wise. Then we have to do double interpolation. And double interpolation is something like this. Look here. Oh, let me go here. Here we go. Okay, here is our problem. Let me give you one example. In this example, we want to find the pressure for the case when the temperature of the water is 320 degrees Celsius and the specific volume is 0.2 cubic meter per kilogram. What we do is this. We first interpolate between the pressures and then between the temperature and then between the specific volume. What does it mean to interpolate between temperatures? It means that we go to the table and we find out that we have 300 degrees Celsius and we have 350 degrees Celsius. Okay? If we look at these two temperatures, when the pressure is 1200 kilopascal, we have the specific volumes. And the specific volume is 0.2134 and 0.2345. In the case when pressure is 1400 kilopascal from your textbook, you can check it. In the case when pressure is 1400 kilopascal, at 300 degrees Celsius, the specific volume is 0.1823, and at 350, the specific volume is 0.2345. 2003. Okay, the value that we are given, specific volume equals zero point 0.2, is actually something between these four numbers that we have found here, right? It is surrounded by these four values, these four, right? Our specific volume is surrounded by these four. So we have surrounded it. Now we want to find it. Okay, let's check it this way. Here it is. Oh, my apologies. What did happen to this? Okay, go back. All right. All right. Here we go. Oh, okay, let's go back here. Okay, here we go. All right. At the first step, I look at each constant pressure and interpolate the V at the given temperature, 323 degree. If I interpolate 320 degrees Celsius at 1200 kilopascal, just look at 1200 kilopascal. At 1200 kilopascal, right, for the given temperature, 323 degrees Celsius, I can interpolate and find that specific volume is 0.2231. Then I only look at the pressure of 1400 kilopascal. At 1400 kilopascal, when the temperature is 323 degrees Celsius, I can interpolate and find that the specific volume is 0.1906. All right? Now the next step. The next step is this. I have fixed the temperature, I'm done with it. Now the next variable is the specific volume. Just put away the temperature from this table, right? Put away temperature from this table, and then at the next step, you will have such a table. You know that at 1200 kilopascal, V is 0.2231. At 1400, it is 0.1906. Now we are looking for the case when it is 0.2, right? Something between these two. And now I go and find the corresponding pressure when specific volume is 0.2. If you do the interpolation, then you will find this value. Keep in mind that we previously had taken care of temperature. So I know that temperature is 323 from step one. From this step, I found that pressure is 1342 kilopascal. This is what we call double interpolation. As you see, this is a time-consuming process. Both single interpolation and double interpolation are time-consuming processes. So what I want you to do is, all of you, to use your calculators. Find the function that your calculator have for interpolation and try to solve interpolation problems using calculators. In order to make sure that you are solving them correctly, you can solve a couple of problems by hand and then use your calculators to double check and see if it agrees or not. Keep in mind that in our course and in all thermodynamic courses, for many problems you need to do interpolation, right? Or extrapolation, which is similar to this, but with the difference that in extrapolation, the number that you are looking for is out of the table, okay? But the formula will be pretty much similar to this. All right, I want you to use your calculators and do this, because during the exam and in your work as professional engineers, you're not going to have time to sit and do these calculations by hand. Because for any problem, you might need, for instance, for a very simple cycle, any simple cycle consists of four states. And if you want to do interpolation for four states, it means that you're going to do this calculations at least 4 times. Most of the time, for each state, you need more than one property, which means that you're going to calculate at least 8 or maybe 12 interpolation and sometimes 12 double interpolation. This is really time consuming. So practice using your calculators, right? And try to use them effectively, both for your homework and later for your quiz and exam. All right? All right, let me go. Oh, okay. For the next one, let's call it the end of the day, and then we are going to go over next uh, slide. No, my apologies. We are going to go over next presentation files. By the way, I'm going to upload a new updated version of this lecture 8, and please use that one, okay?